Well, welcome back. We are now working in chapter 3.5. 3.5 is based upon inverse trigonometric functions. That's right. We're going back and looking some of that trig stuff again. As we've been mentioning all semester long, how important it is to know your unit circle and exact values application, it's coming back to haunt you once again. So here is my standard unit circle we printed out for you guys. And just remind you, when you're looking at the unit circle, x is equal to the cosine of the angle. The x-coordinate of your particular point is the cosine of the angle. Y is the sine of the angle. The y-coordinate is the sine of the angle. And if I do y divided by x, that is actually going to give me the tangent of the angle. So the ratio of the y-coordinate over the x-coordinate is the tangent of that particular angle. So when I say, what is the sine of pi 6? The sine is the y-coordinate at pi 6. Here's pi 6, so the y-coordinate is 1/2. So therefore the sine of pi 6 is 1/2. The cosine of cosine of 7 pi 6, find your angle, 7 pi 6, the cosine of it is going to be the x-coordinate, which is the negative square root of 3 over 2. Another problem would be maybe the tangent of 7 pi fourths. So I look on my unit circle until I find 7 pi fourths down here. I want the tangent of it, so I'm going to take the y-coordinate divided by the x-coordinate. So the y-coordinate is negative square root of 2 over 2. The x-coordinate is positive square root of 2 over 2. So negative square root of 2 over 2 divided by positive square root of 2 over 2 is 1. So the tangent, or the negative 1, excuse me. So the tangent of 7 pi fourths is negative 1. But now, that's something that we all done way back when in those trig classes and stuff. What we're interested in is inverse trig functions. So, to rewrite this type of thing, this is what's going on. The cosine inverse of the x-coordinate is going to give me the angle back. The sine inverse of the y-coordinate is going to give me the angle back. And the tangent inverse of the y-coordinate over the x-coordinate gives me the angle back. So what inverse trig functions are is you give me the ratio and it gives me the angle back. Now the problem with inverse trig is, there's more than one answer when I take a sine of an angle that gives me the same y-coordinate. For example, the sine of pi fourths, is square root of 2 over 2. And the sine of 3 pi fourths. 3 pi fourths is also square root of 2 over 2. So there's two different angles that gave me the same y-coordinate. So that's going to cause us a little bit of problem with taking the sine inverse of a number and getting back the angle. Which angle do we want? The pi fourths or 3 pi fourths? So what we have to do here is this. We actually have to go and do what we call the restricted unit circle. So the restricted unit circle is this. When you're talking about doing the sine inverse of a number to get the angle back, or the tangent inverse of a number to get the angle back, or the cosecant inverse of a number to get the angle back, you've got to use the restricted unit circle of just using the right half of the graph, just this side of the graph, between pi halves and negative pi halves. So down here, we get negative angles. So this will be negative pi 6, negative pi fourths, negative pi thirds. And we only use the right half of the unit circle. So for sine inverse, tangent inverse, or cosecant inverse, we only use this half of the unit circle. And we have to redo these angles. These angles would be negative pi 6, negative pi fourths, and negative pi thirds, and this angle here would be negative pi halves. Okay, that's for these guys. And if I happen to do the other three trig inverse functions, the cosine inverse of a number to get the angle back, the cotangent inverse of a number to get the angle back, or the secant inverse of a number to get the angle back, on your unit circle, you use the top two quadrants, quadrant 1 and quadrant 2. So the top two quadrants over here is what you would use when I'm looking for cosine inverse, cotangent inverse, or secant inverse. So, again, playing with our unit circle and knowing our restrictions here, let's see if we can do these particular problems. What is the exact value of the cosine inverse of 1/2? Being a cosine inverse, I get to use the top half of my unit circle. Cosine is the x-coordinate. Where is my x-coordinate equal to 1/2? X-coordinate half is right here. The x-coordinate, the autofocus works, you can see it. X-coordinate is 1/2. And remember, when you're asked about an inverse trig function, cosine inverse, sine inverse, tangent inverse, secant inverse, cosecant inverse, cotangent inverse, the answer is the angle. And we're typically doing our stuff in radians because we're science class. We do it in radians. So the cosine inverse of 1/2 is pi thirds. So my answer is pi thirds. So what would the cosine inverse of negative square root of 2/2? Well, again, it's cosine inverse, so I would use the top two quadrants. Cosine inverse is restricted to the top half of your unit circle. And once again, letting the autofocus work, see if you can find where the cosine is the x-coordinate. Where's the x-coordinate equal to negative square root of 2/2? It's located right here. X-coordinate is negative square root of 2/2, which gives me the angle of 3 pi fourths. So my answer is 3 pi fourths. Now, let's keep on going here. Find the exact value of the sine inverse of 1/2. Remember, also to let you guys know, when you hear sine inverse, or this could also be written as arc sine of 1/2. So sine inverse, arc sine, same thing, of 1/2. In other words, the sine of what angle equals 1/2? We want the angle back. Now, so I'll go to my restricted unit circle here, but now it's a sine inverse. Sine inverse, we only get to use the right half of the graph, and the fourth quadrant ends up being a negative angle. Sine is the y-coordinate, so where's the y-coordinate equal to 1/2 at? It's right here, and so the angle is pi 6. So I get to go back and rewrite this answer as pi 6. And this next one is what messes people up, got to be careful. So what is the sine inverse of negative square root of 3/2, also known as the arc sine of negative square root of 3/2? Well, what angle is that? Well, let's see here. We're trying to figure out the angle. Remember, sine is the y-coordinate, so, but for sine inverse, we want to use the right half of the graph. So where's the y-coordinate equal to negative square root of 3/2? Well, there's a positive up here, y-coordinates, they're negative down here. There's negative square root of 3/2. So the answer is, well, remember, now it's not 5 pi thirds because with the fourth quadrant using, you have to use the negative angles. This would be negative pi thirds. So the answer is negative pi thirds. What about this one? Give the exact value of the tangent inverse of the square root of 3. Now we're talking about these exact values, so you should be familiar with these. You know, ones and zeros is square root of 3/2s and 1/2s and the like. So for the tangent inverse, or arc tangent, if you will, of the square root of 3, remember, it's the y over the x. So I'm trying to use these exact values. The only thing that has a square root of 3 in it is that square root of 3/2 stuff. So if I want to write this guy in terms of square root of 3/2s and 1/2, you will notice that it's the same thing as the tangent inverse of the square root of 3/2 divided by 1/2. Because when I have a fraction, I invert and multiply, and notice the 2's cancel, so this and this is the same thing. But this helps me out a little bit better because this is the y-coordinate over the x-coordinate. So where is the y-coordinate square root of 3/2? Where's the x-coordinate 1/2? So, again, tangent inverse, we're looking at the right half of the graph, so there's only half the number of points I need to inspect here. I want the y-coordinate to be square root of 3/2. I want the x-coordinate to be 1/2, so what angle is that? Pi thirds. Okay, similar problem. What is the tangent inverse of 1 or the arc tangent of 1? Well, remember, this is still the tangent inverse of a y over x. The ratio has to be 1, which means x and y are the same thing. So if you ever look at your unit circle and have it memorized, as you should, where's the x and y the same? Well, it's at those square root of 2 over 2, square root of 2 over 2 things here. So again, I'm looking at the right half of the graph. So this is going to be, to get that ratio of 1, is the same thing as the tangent inverse of the square root of 2 over 2 over the square root of 2 over 2, ratio of 1, which gives me the angle of pi force right here. Well, let's do some limit kind of problems. What is the limit as x approaches infinity of the tangent inverse of x? Well, to really get into that, you actually need to go back and look back at the graph of y equals to tangent of x. And if you remember, you had two asymptotes here, negative pi halves and positive pi halves. And this is my y-axis, my x-axis, and remember your tangent graph looked like this, and then it continued to repeat. Okay? So this was your tangent graph. And you'll notice that when we talk about one complete period, it's between negative pi halves and positive pi halves. And where, remember, this is the tangent inverse. This is actually the original graph of the tangent, and my question's about the tangent inverse. But you'll notice here that my graph blows up and going towards infinity at what angle? Positive pi halves. So, in other words, we have this. The tangent of pi halves, slightly from the left, because I'm less than pi halves, is equal to infinity. So if you want to really rewrite this, this is equivalent to saying pi halves, officially from the left, equals the tangent inverse of infinity. So when I take the limit as x approaches infinity of the tangent inverse of x, what am I going to get? Pi halves. And similarly, I'm shooting down here between negative pi halves and pi halves. The tangent graph shoots towards negative infinity as I get closer to negative pi halves. So the tangent of negative pi halves, officially from the plus side, is going towards negative infinity, which is equivalent to saying that negative pi halves from the plus side is equal to the tangent inverse of negative infinity. So when they ask you the question, what is the limit as x approaches negative infinity of the tangent inverse of x? Well, what angle do I get when I take the tangent inverse of pretty much negative infinity? The answer is going to be negative pi halves. So in this section, it's a reviewing of the old unit circle and looking at it from the inverse trig perspective. But what we're really after is those darn derivatives. So that's what the second part of chapter 3.5 is about, and that is about taking the derivative of these guys. Now the key to math is catch a pattern. So let's see if you guys can catch a pattern. So the derivative of the sine inverse of x is 1 over the square root of 1 minus x squared. The derivative of the cosine inverse of x is negative 1 over the square root of 1 minus x squared. The derivative of the tangent inverse of x is equal to 1 over 1 plus x squared. The derivative of the cosecant inverse of x is negative 1 over x times the square root of x squared minus 1. The derivative of the secant inverse of x is equal to 1 over x times the square root of x squared minus 1. And the derivative of cotangent inverse of x is negative 1 over x plus 1 plus x squared. So the key to this is, it looks like, oh no, a lot more formulas memorized. Well, you're right. But actually, there's only really 3 formulas you need to memorize, and you need to catch a pattern. Have you caught the pattern yet? Well, the pattern is this. The derivative of sine inverse of x is 1 over the square root of x, or 1 minus x squared. The derivative of cosine inverse of x is negative 1 over the square root of 1 minus x squared. It's the same formula, but when you took the derivative of the cosine inverse, it was negative. Look at the tangents. The derivative of the tangent inverse of x is 1 over 1 plus x squared. The derivative of the cotangent inverse of x is negative 1 over 1 plus x squared. The derivative of the co is negative. Look over here. The derivative of the secant inverse of x is 1 over x times the square root of x squared minus 1. The derivative of the cosecant inverse of x, being a cofunction, is going to be negative 1 over x times the square root of x squared minus 1. Same function, but every time I take a derivative of a co, it's always negative. That's the pattern. Now, but as I mentioned to you guys before, every time you take a derivative of one of these things, you have a rule and you got the chain rule version of it. So, the derivative of the sine inverse of x is equal to 1 over the square root of 1 minus x squared. That's the rule. But if I have this, if I said y equals the sine inverse of a function, then we got to use a chain rule version of it. So every rule, there's a rule, and then there's a chain rule version. The chain rule version would be the derivative of sine inverse of a function is 1 over the square root of 1 minus the function squared times chain rule, the derivative of the inside. So if I have y equals, obviously, the cosine inverse of x, that implies that y prime is negative 1 over the square root of 1 minus x squared. And if y equals the cosine inverse of a function, then y prime equals negative 1 over the square root of 1 minus the function squared times the derivative of the inside. Notice it's the same thing. But you got the rule and you got the chain rule version of it. And because of this, I don't feel the need to actually write down the co-inverses. Just got to write down the big formulas. So if y equals the tangent inverse of x, or arctangent of x, then y prime equals 1 over 1 plus x squared. Then you got a chain rule version of it. If y equals the tangent inverse of a function, then y prime equals 1 over 1 plus the function squared times the derivative of the inside. And cotangent is going to work the exact same way, except it'll be negative. And then the third one here is y equals the secant inverse of x. We have that one memorized as the derivative is going to be y equals 1 over x times the square root of x squared minus 1. Key to math, catch a pattern. So if y equals the secant inverse of a function, then y prime is equal to 1 over the function times the square root of the function squared minus 1. Chain rule times the derivative of the inside. So we're replacing all the x's with the function times derivative of the inside. And of course, if you took derivative of the cosecant inverse of x, it would be derivative would be negative 1 over x times the square root of x squared minus 1. And therefore, the derivative of the cosecant inverse of a function, the derivative would be negative 1 over the function times the square root of function squared minus 1 times f prime of x, the derivative of the inside. So, let's see if we can do a few of these problems. The first one, again, give you guys a little different looks of how we can ask you guys to take derivative. This is our Leibniz notation of taking derivative. D dx, which means take derivative of the function that follows. It's just equal to, what's my derivative? What is derivative of 5 times the secant inverse of x plus 2x squared plus 3? Well, derivative of 5 is constant, leave it alone. Derivative of secant inverse of x was that 1 divided by x times the square root of x squared minus 1, pure memorization, plus derivative of 2x squared is 4x, and derivative of 3 is 0. So there you go. You can probably clean it up by putting the 5 up top, but that's all you needed to do. Next one is find the derivative of 5 times the cosine inverse of 3x squared plus 5. Now, this is a cosine inverse of a function. It's not just of x. Cosine inverse of x is at negative 1 over the square root of 1 minus x squared because it's a cofunction. But we have to use the chain rule version of this guy. Now, 5 is being multiplied as a constant. Constants hold over, so leave that 5 right there. What's the cosine inverse of a function? Well, it's going to be times negative 1 because it's a cofunction. A negative 1 divided by the square root of 1 minus the function, which is 3x squared plus 5, the function squared, times the derivative of the inside. The inside is 3x squared plus 5. That was my function. Derivative of that function is 6x. Now, of course, you really probably want to clean this up, putting my constants together. 5 times negative 1 times 6x is negative 30x divided by the square root of 1 minus 3x squared plus 5 squared. And let's do one more of these guys. The derivative of the tangent inverse of 5x squared plus 17. Again, it's the tangent inverse of a function. If it were taking the derivative of just a tangent inverse of x, the formula is 1 over 1 plus x squared. But we have a function here, so my derivative of tangent inverse of a function is 1 divided by 1 plus the function, which is 5x squared plus 17 squared, times the derivative of the inside. Chain rule. Derivative of 5x squared plus 17 is 10x. And again, if you clean this guy up, you end up getting 10x divided by 1 plus 5x squared plus 17 quantity squared. So now we're beginning to learn how to take the derivative of the inverse trig. Arc sine, arc cosine, arc tangent, arc secant, arc cosecant, arc cotangent. So, and then, of course, we're going to, as we get heavier into this particular section, we'll be looking at rates of changes, the equation of tangent lines, and some of the applications that we can do with this stuff. So, again, more functions to memorize and remember, just like I said before. For every rule you have to have memorized, there's a rule, and then there's the chain rule version of this thing. So, and these are your basic rules for taking the derivative of your inverse trig functions. So, hope this has been helpful.